Okay, so what we have seen so far is one of the approaches to motive finding using computational means, right. So, we have seen that in computational motive finding, there are two approaches that we are going to look at. One is called word enumeration based approach, where we represent a motif as a pattern or a k-mer, right. So, here we represent a motif as a pattern or k-mer, and then we go over all the 4 to the k possible k-mers and look at which of these k-mers or which of these patterns best represents the set of sequences, right. So, is over represented in the set of sequences that are provided as input. Okay. So, that is a word enumeration based approach, and we saw that this median string problem gives you a good algorithm to solve this problem. This was also called as the equivalent motive finding problem. And we saw that we could solve it in order of 4 to the k, because there are 4 to the k k-mers, and each of the k-mers you are testing if that is enriched in the set of strings that are given as your input DNA sequences. Okay. These are the DNA sequences that are upstream of your target genes, and all of these target genes are bound by the same transcription factor, right. So, you have 4 to the k is all the possible patterns that you could have of length k, and then you have nkt. For each pattern, you will have to go through all your t input strings in your set of DNA sequences that are given. So, there are t DNA strings that are given, each DNA string is of length n, right, and then k is the length of your k-mer, right. And so, this much amount of time is required to figure out what is the best matching k-mer in a particular string, right, in each of the t strings for a particular k-mer pattern that you are interested in, right. So, this we saw was much better than certain earlier solutions for brute force solutions for the motive finding problem. This equivalent motive finding problem using the median string gave us this good running time, but still this is pretty slow if k is large. Okay. If k is small, maybe k less than 10, 11 and so on, this will work very nicely, but if k is 20, then we need some other algorithms, possibly heuristics, to look at it. Okay. And that is where the second approach comes in. So, the first approach is this word enumeration based approaches. The second approach is going to be profile based approaches or position weight matrix based approaches. Here, how do you represent a motif? You represent a motif as a profile which we will see next, or specifically a position specific weight matrix. Okay. So, it is also call it as PSWM, position specific weight matrix. Okay. Each of the positions, each of the letters in your k-mer pattern, right. So, each of the k positions you associate a probability distribution on what is the likelihood that it is an A, C, G or a T. Okay. So, you have a probability profile or a position specific weight matrix or frequency matrix. Once you represent motif as this matrix, then your algorithms are basically at each step you update your profile, update your position specific weight matrix, and using that you update your set of motifs, and then you keep on iterating this until you get a good set of motifs that you are interested in, that captures the motifs, the patterns that are enriched in your input set of tDNA sequences. Okay. And so, the profile based approaches, we will mainly look at a randomized approach. So, this randomized motif search and also a Gibbs sampling based approach, both of them are randomized algorithms. But before we see that, let us just look at what a profile is in the context of a greedy motif search. Okay. So, this greedy motif search, the next topic, we will look both what a profile is and a greedy algorithm that greedily updates the profile. Okay. So, that will set the stage for what we actually want to look at, which is your randomized algorithms, both based on a simple randomized motif search and based on Gibbs sampling, to figure out your best set of motifs that are over represented in a given set of input DNA sequences. Okay. Okay. So, let us get started with what a profile is. A profile is simply a frequency matrix or a counts matrix. Okay. So, if you look at this particular motifs, Again you will have to remember that these are all your T strings, T input DNA strings, T strings that are provided as inputs, we called it as DNA, right. And among these T strings we are figuring out a set of motifs, right. So, all of these T strings are here, and then you are saying that the motifs are over here, over here, over here and over here. So, you are given these T strings, right. So, S1, S2 etc. to ST, and then among these T strings you have figured out some locations where the motifs start, right. So, these are all k-mers from each of these strings, and these are all the locations where it has started, and you are now aligning all of them up, and then so here you have all the k-mer positions, right. So, these are the k-mers. So, this is basically a T cross K matrix, right. So, you have the T strings and then the k-mers, one from each string that has been selected, and they are all aligned together, and then you have this T cross K matrix, and that is what we have called as motifs all along. Motifs is simply a collection of k-mers, one from each string, okay. And then you just compute the count of this motifs, and the count of the motifs is going to be simply the ACGT frequency along each column. So, here you can see that there are 10 strings here, right, and then there is 1, 2, 3, 4, 5, 6, 7 of them are T's. So, you put in as 7, and then there is 2 A's and 1 C's, right. So, 2 A's and 1 C's, and then there are no G's. So, this is just simply this particular column's counts of the different letters in that column, okay. And these are DNA sequences. So, your alphabet size is 4, you have ACGT, and then you just do that count, and then these two columns, for instance, you have all G's and all G's here. So, you have 10 and 10, and then everything else is 0, right. So, this is the count of the nucleotide I in column J, right. So, from your T cross K matrix, you have now collapsed it into a 4 cross K matrix, where 4 is the size of your alphabet, right. And now, once you have this count, you can easily normalize each column and then convert it into probabilities, right. So, now you can look at the normalization of this. So, you had like 2107, you just divide it by 10, you will get 0.2, 0.10 and 0.7. Similarly, here we had 10 here, you divide it by 10, you will get 1, and then everything else is 0 for these G columns, all G columns, right. So, you have now the frequency or the probability of nucleotide II in column J, right. So, that is so this is your column J, and then this is your nucleotide I ACGT, right, and then this tells you that this is all G's and there is 1 T. So, there is 0.9, 90% probability that this is G, and then 10% probability that it is T, okay. So, this gives you a nice the position specific probabilities, right. So, that is why this is called a position specific weight matrix, because each of these k positions, these k-mers, k positions is what is shown here, right. So, k positions. So, each of your positions along this motif, you have a weight that are weights that are given that add up to 1, probabilities that are given that is adding up to 1. So, this is a position specific weight matrix or a position specific frequency matrix, also known as a profile, okay, or a probability profile. So, each column of a profile represents, now you can think about it as a 4-sided dice, right, and then with ACGT on the 4 sides, and it has a certain probability of coming up A, C, G or T, okay. Each of the positions will have a differently loaded dice, okay. So, these are not identical dice, but each of these dice have different probabilities of coming up the 4 outcomes that it has on its faces, okay. And so, that is what I just said. So, it means that we have k different dice, each having its own set of probabilities of which one, what is the probability that that particular dice in column J comes up as A, C, G or T, okay. So, given this, then you can always calculate the probability that a given k-mer would be generated by this profile matrix, right. So, if I want to look at this particular k-mer TC, GG, GG, ACT, TCC, right, then you can calculate the probability that this particular k-mer is generated by this particular profile matrix, right, because all you have to do is that this is the first letter is T, so I am going to take 0.7, the second letter is C, I am going to take 0.6, the third letter is G, I am going to take 1 and so on, and then I am going to take all these probabilities and I am going to assume that each of the positions are independent of each other. So, I can just simply multiply all these probabilities under that assumption, and that will give me the total probability of seeing this particular k-mer, right. This is the total probability that this k-mer is generated by this profile matrix, right, and that is what is shown in an example here, right. So, we have a smaller k-mer here. So, k is 6 here, AAA CCT. I want to know what is the probability that AAA CCT is generated by this profile matrix shown here. Okay. And so, that is as I said, you just look at this first A and then you look at this 1 over 2, the second A you look at this 7 over 8 in the second position, the third A you will have to look at the third column in the profile matrix and look at the corresponding entry for A, that is 3 over 8, and so it is going to be simply this for this A and this A, then you have CCT. So, this has to be C, this is another C, and then you have a T which is 7 or 8, right. So, all of these circled red numbers, if you multiply them together, then you will get the probability that this profile matrix that is shown here in the top generates the k-mer AAA CCT. Okay. When you throw this set of k dice. Okay. So, the probability that this set of k dice will generate AAA CCT is going to be the product of all these numbers. Okay. And that is what is exactly shown here. So, those numbers are all given in colors here, red colors for A, blue colors for C, and then green for T. And so, you have this multiplication of all of these numbers, and then that gives you 0.033646. Okay. You can also ask this for other k-mers that are going to be generated by this profile. So, if you have 80A CAG instead of 3 A's and CCT, then you can look at again looking at 1 over 2 here, but then instead of 7 over 8, now I have to look at the second letter is 1 over 8, right, third letter is A, fourth letter is C, A, G. So, then all of these colored entries here in the profile matrix, I will have to multiply it and then I get 0.001. So, this is lower probability than the other one. So, the 3A CCT, that k-mer is higher probability than the second k-mer, okay, 80A CAG. And you can also see here that based on these few examples, you could probably also generalize and say that the closer the k-mer is to the consensus string, right, the larger the probability of the k-mer is according to this profile. Okay. And so, because the letters in the consensus string are going to get the highest probability in each of these columns, right. So, then the closer you are to the consensus string, you will get the higher probabilities. So, we have converted our scores that are based on how many letters disagree between a particular k-mer and the consensus string to what is the probability that a particular k-mer is generated by a particular motif matrix. So, this gives you a probabilistic based scoring. And so, using this scoring, then given a sequence and given this profile matrix, right, you can figure out what is the k-mer in the sequence that best matches this profile, right, and that is what is going to be shown next. So, you have a profile, let us make a simple definition. So, the profile most probable k-mer in a sequence is the k-mer with the highest probability of k-mer given profile, okay, among all the k-mers in the sequence. So, if your sequence is of length n, right, if your sequence is of length n 1, 2, 3 etc. to n, then you know that there are all these different k-mers, right, that start at different positions, and there are totally n minus k plus 1 k-mers in this sequence, right. So, among all of these n minus k plus 1 k-mers in the sequence, I want to know which k-mer has the highest probability of k-mer given a particular profile matrix. Okay. In this particular example, this is my profile matrix that is given. Somehow someone has given me this profile matrix and given me a sequence, and they want me to know among all of these k-mers which k-mer has the highest probability of k-mer given profile. Okay. And that particular k-mer, I am going to call it the profile most probable k-mer in the sequence. It is the most probable k-mer in the sequence according to this profile. Okay. So, the profile most probable k-mer in the sequence, and then let us say our sequence is this, right. Then I want to know what is the profile most probable 6-mer, k equal to 6 in this sequence. Okay. Let us just tabulate it and then do it. So, here all of the 6-mers in this particular string CTA, TAA, this particular string shown in the top, right, is given here, the probabilities of all of the 6-mers according to this profile matrix. Okay. You can see here that many of them are zeros, the first ones, because if you look at CTA, TAA, right, if you look at CTA, TAA, then you are looking at C here, T here, CT, A, right, and then TAA, right. So, this is going to be T, this is A, and this is A, right. So, there are two zeros that I have circled, and so multiplying all of these together will end up with a 0. So, that gives you 0 for the first k-mer. Similarly, the second k-mer also has a 0 probability, because if you look at this particular profile matrix and look at the third letter, for instance, which is TAT, right. So, in the third column here, right, T has a 0 probability, because of which this third entry here is 0, and then everything else whatever it is, it does not matter, it will just multiply it by 0, you will get 0 again, right. So, many of these are 0, but luckily there are 3 entries which are non-zero, right, and then one of them is this AAACCT, right, and that we have already calculated its probability in the previous slide to be according to the same profile matrix 0.0336, right. And then you have these other things which are 0.0299 and 0.0004, other things are 0. So, this is your most probable k-mer in this whole sequence, right. So, this is your profile most probable 6-mer in this whole sequence that starts at this position 1, 2, 3, 4, 5, the 5th position, and then the actual k-mer is AAA CCT. Okay. So, this gives you a way to take a profile and then look for the k-mer in a sequence that best matches this profile, right. So, that that has the highest probability according to this profile. Okay. And once you have that, then you have a greedy algorithm that can figure out the best set of motifs in a given set of input sequences, right. So, you have T sequences, you look at some way of initializing the very first sequence, randomly setting the very first motif in the very first sequence. Okay. But given that you are at a certain point in the algorithm where in the first I minus sequences in your set of all T strings DNA, you have figured out the locations of these k-mers, motifs, motif 1 etc. to motif I minus 1, then you can form a profile from these already selected motifs. Then you can add one more motif, the ith motif, by adding the profile most probable k-mer motif I in the ith sequence. Okay. So, if the ith sequence is as in the previous slides CTA, TA and so on, the sequence shown on the top here, then your profile most probable k-mer motif I in this ith sequence will be AAA CCT, right. So, that you add it as motif I, and once you add that as motif I, then you have from I minus 1 motifs, you now have I motifs. Then you can iterate and you can go back and update your profile, you can form your profile from all of these I motifs, then you can go to the I plus 1th string and then you can figure out the best motif there. Okay. So, this is a simple greedy algorithm that is immediately implied by looking at profile representation of your motifs and then looking at what is the profile most probable k-mer in an input sequence. Okay. But like I said, greedy algorithm is not really our end goal, because it's not fully satisfactory. We want to look at randomized algorithms that toss a coin internally and then make decisions internally based on the outcomes of these coins or coin tosses or die rolls. Okay. So, and they have certain advantages over greedy algorithms in these problem settings. So, let us just look at how to do randomized algorithms given that we know what a profile is.